Welcome to my cycle tempo tutorials. Here I will show you how to calculate several configurations of Rankine cycle. So in this tutorial we are gonna model a Rankine cycle. So the Rankine cycle will consist of a boiler, a turbine, condenser, two pumps, and feed water heater, which serves also as the aerator. Additionally, we need to have a heatsink for our condenser for the rejected heat. So we will connect the components. Where for liquid water we are using stream cold water. And for the vapor phase we will use vapor. Now we will need to set up our parameters, where in boiler we will say that the outlet pressure is 9 megapascal, 90 bars, pressure drop 0, outlet temperature 550 degrees C, and efficiency of the boiler is 0.85. Then for the turbine we need to put in some isentropic efficiency, so we will use 0.87. Eventually you can also specify mechanical efficiency for the turbine, or we can add a generator connected to the turbine by a shaft, and at the generator component we can also specify efficiency of generator, so let's put there 0.99. Now moving on to the condenser, so we will need to set pressure differences across the condenser. Let's use zeros for both delta P1, which is on the cooling water side, and delta P2 on the condensing vapor side. We can specify directly pressure of our condensation, so let's put it here, 0.04, and let's say that we want to have temperature difference at the hot part of the heat exchanger, which means we can have a look in the reference guide. Let's search for condenser. So here we have condenser. Just to remind you, this is primary side, this is secondary side. And delta TH is the temperature difference at the hot side of the heat exchanger, meaning between the cooling water outlet and the condensing steam. And we will specify this value as 3 degrees Celsius. Additionally, we can say that we want certain subcooling, like 5 degrees C. Now moving on to the pump. At the pump we need to specify isentropic efficiency. Let's put 0.8, and we can also specify mechanical efficiency and electrical efficiency. The same goes for the other pump, but here just to demonstrate that we need only isentropic efficiency for the model to work, so let's put there just that. Moving on to the aerator, we need to set pressure difference across the aerator, and we will say that the aerator is at temperature of 105 degrees C. So the boiler was already set up, and at last we need to specify some parameters for our heatsink. So outlet pressure, let's put 1 bar, pressure drop across this component, and outlet temperature, let's put 20 degrees C. So that should be everything. We can run our model, and we got one error. And our error actually says that we are missing one equation for the model, or one parameter. That is true because we have not specified what will be our power output or power input. We can do that by going into general data, production function, and we will say that we want apparatus number 2, the turbine, to have power output of, let's say, 60 megawatts. Once we set it up, so our model is running, we can check the parameters. Turbine inlet 90 bars, condensing pressure 4 kilopascal, meaning 29 degrees C. We got the bleed steam from the turbine at 105 degrees C, 1.2 bars. Now, if we don't want to specify the condensing pressure, but we want it to be function of a specific temperature, so we can do that as well. We can say that we want the temperature difference, for example, for our cooling water to be exactly, let's say, 10 degrees C. So delta T1, temperature difference, here will be 10 degrees C. We keep other parameters, just delete the pressure, and we can run our model. Now you can see that we had temperature from our heatsink at 20 degrees C. It's returning at 30 degrees C, and we wanted minimum temperature difference as 3 degrees C, so condensing temperature is actually 33 degrees C. Now we will update our model by more feed water heaters. So first we will add low pressure feed water heater. So in our component palette, let's find feed water heater, turn it by right mouse click so that the primary side is for the feed water. Let's connect it. So we want water, and we want steam. And now we will have condensate going into the condenser. But in order to have pressures and pressure drops in the way we want, so let's add there one more component, sink or source, which will act as a pressure separator, or as, let's say, throttling valve between the feed water heater and the condenser. Otherwise, actually the condenser pressure would propagate on this line towards the feed water heater, and the calculation would not run correctly. So what do we want to set up in our feed water heater? Again, always we need to specify pressure difference or pressure drops. So delta P1, delta P2, let's put zeros. We will want to specify what is our required outlet temperature at the feed water outlet, node 10. So let's say 65 degrees C. And we will say that we want temperature difference at the high temperature side of the heat exchanger to be 5 degrees C, and the same to be at the low temperature side of the heat exchanger. To see what does it mean, let's go to the reference guide and find the feed water heater. So here you can also see and make sure what are primary and secondary inlets or outlets. And let's have a look at the QT diagram, where the delta TH is the temperature difference between the condensing temperature and primary feed water outlet, and delta T low between the outlet of the outlet temperature of the condensate, either saturated or subcooled, and the inlet temperature of the feed water. So now we have clear how this apparatus works. Just here we did a little mistake. This is delta T1, how much the temperature would increase. We wanted to specify directly the outlet temperature, so here would be 65 degrees C. And now we are missing to specify this component. So for now, let's put both delta P0 and delta H0, like zero difference in enthalpy and zero pressure drop. When we calculate it, so we see no warnings, no errors, and our problem is successfully solved. We can see that we have here outlet temperature of 65 degrees C, that the steam bleed is at 0.3 bar, and actually the 0.3 bar stays also here. But in the case that we have shown previously, where we would specify directly the pressure at the condenser, meaning here, for example, 0.04, and we would not specify the heating up of the water from the heatsink. So now, in this case, however, if we would delete this component and just connect it with the water stream, so running the problem, we get 3 warnings, and looking at the warnings, we actually see that there are negative mass flow rates and crossing of temperature profiles in the heat exchanger number 8. we can have a look at the Qt diagram. And we can see that really this could not work because the steam pressure sets at the, as you can see, at the condensing pressure. So if we specify the pressure in the condenser, we need to have that intermediate component as which can act the source or sink. But if we specify the condensing pressure by, not directly, but by temperature difference of the cooling water and some pinch point, so the problem works, or the calculation of the problem works well. Now we can add second feed water heater, which will be on the high pressure part. And take steam. And now actually we will demonstrate how, here we have the condensate cascading into the condenser. Here we can demonstrate pumping of the condensate upstream of the flash heater. So we will add a pump, and our condensate will go via pump into the junction component, or also acting as a mixer, and from there into the boiler. So what do we set up here? Again, pressure differences, let's put zeros. Here we can, let's put delta T as temperature increase as 60 degrees. Let's try to specify here the condensing pressure directly as 10 bars. Pumps need to have some specification of isentropic efficiency. And in the mixer there needs to be specified pressure drop, which here will be, which we will use as 0. Running the problem, we get now 3 errors, and we can see that actually the program cannot calculate temperatures at points 13, 15 and 17. The problem is how we specified the heat exchanger, how we specified the feed water or flash heater. We did not set any temperature differences, nor did we set the state of the outlet condensing steam. So here we will specify that the steam at the outlet is exactly at the point of saturated liquid, putting satcot equals to 0, and we have problem. Our problem is being solved without an issue. We can see system efficiencies, that our plant has efficiency of roughly 34%. We can have a look at view, new graph, Qt diagram, and we can have a look at the process of heating up of the feed water. So let's put there first the node 10, then flash heater 9, the aerator 6, and flash heater 8. And we can see how the feed water is being heated up, while there is a little bit of the node, the mixing point. Then we have the first flash heater, where the steam input is superheated. Then it condenses, and there is no subcooling. Same is the case for the aerator, and for the low pressure feed water heater, we specified minimum temperature difference between cold inlet and hot outlet, so there is certain subcooling. Lastly, I will demonstrate how to put reheater. So let's add into our configuration one more turbine and the component reheater. So connect high pressure part of the turbine, high pressure turbine outlet to reheater, and reheater outlet to low pressure turbine. So now for the turbine we will always again specify some isentropic efficiency, 0.87 for example. We can connect all the turbines to single shaft. And for the reheater, so we need to specify outlet temperature. Let's use the same as was in the case of boiler, 550. So here for the reheater, P out 550. We need to specify pressure drop across the component, and then we need to specify the intermediate pressure, either inlet or outlet. We can put 15 bars. Let's calculate our problem, and we should be able to see that our efficiency actually went a little bit higher. Here we go. System efficiencies. Before we had efficiency about, I think about 33%. Now we have about 36%. If you would like to specify a pressure drop in the turbine bleed stream, you can do it actually by clicking on the stream and add extra condition and specify either delta P, as we can put here 0.1 bar, or specific, we can also specify here the pressure inlet or pressure outlet respectively. So once we did it, we calculate the problem. We can see that while the condensing pressure here is 0.3 bars, so here it's 0.4. And lastly, we can show the entire cycle in TS diagram. So we can put in new graph, TS diagram. In contents, we can select pretty much everything. Just some parts, as the cooling water, they will not be really visible on it. And we can see our cycle in TS diagram, where we can see the reheating, we can see the turbine bleeds for the feed water heating, and the cycle in general.